This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Jeff Meyerson. Haoyuan Li is the creator of Alluxio. Haoyuan was a member of the Berkeley AMPLab, which is the same research facility from which Apache Mesos and Apache Spark were born. Haoyuan also goes by HY. HY, welcome to Software Engineering Radio.
Thank you, Jeff. Thank you for the invitation.
Absolutely. Thanks for coming on. So you've said that memory is a king, and there is a trend that motivates you to say that memory is king. So the cost of memory and disk capacity are both decreasing every year, but only the throughput of memory is increasing exponentially. So give some more color on this trend. Why is the growing throughput of memory so important to the big data stack?
Yeah, exactly. That's a great question. So what we are seeing is, as you said, both memory and disk price goes down, and the memory price goes down like by 50% every 18 months. And on the other side, only memory performance is still increasing exponentially every year. So why this is important? Because the data is also growing exponentially. So this means that the memory speed will keep growing along with the data size growing. So you can do more data access by exponentially more data access at the same time. That's the reason why this trend is so important, why we're saying memory is the king. And from a Luxio perspective, because we see this and we view memory as the primary storage media, and we design our architecture to be a memory-centric architecture to leverage memory performance as much as possible. That's the thing we're seeing, and this trend, like at the beginning of 2000, like Wall Street companies, they started to leverage the memory DRAM aggressively, and in 2010, around that time, the company like Baidu, like Google, those internet giants, they start to leverage the memory aggressively as well. And what we are seeing is now the whole industry is moving into this direction, and we are the leading memory-centric solution for storage.
Before we get into talking about Alluxio in more depth, I want to first talk about file systems and storage to get a historical context in order to understand the breakthroughs that Alluxio makes. So let's go into the past a little bit. Historically, we've had to make trade-offs along what is called the memory hierarchy. Could you give a brief overview of how the memory hierarchy has evolved and how this relates to the modern Hadoop or the modern big data stack?
Yeah, so traditionally, a lot of storage systems in history, and in some of these storage systems, they have the hierarchy. They all have the hierarchy, and even inside of every single machine, you have level 1 cache, you have level 2, level 3, you have DRAM, and then you have some storage in your PC, in your laptop, like SSD, like disks. So basically, it's just people put hotter data in the higher layer in the hierarchy, and to leverage their performance. That's what has been happening. This has been true since the beginning of the storage systems. So, but what recently really happened is that, along with the increase of the memory capacity, along with the popularity of the distributed computing, as well as the increase of the data size, what we are seeing is that because of the larger memory, like every single machine, they have more memory space left for storage for storage. So what we're seeing is that a lot of companies, they are buying machines with a 256 gigabytes memory or even half terabytes memory per server. So when you have a server, when you have a cluster of these type of servers, like 100 servers, so you will have 50 gigabytes memory space you need to manage. And it's very intuitive in this sense that we need to have a storage system, distributed storage system, which can leverage this giant memory space. Yeah, so that's the thing we're seeing. And because this space is much, much larger, it's very intuitive for people to be able to leverage this bigger and bigger memory size to do a memory-centric storage and computing.
And if memory usage is getting more appealing, does this mean that we should start migrating all of the functionality of disk to RAM?
It's not really like removing disk from the picture per se. It's more about saying how do we leverage the more and more resource from DRAM. So since DRAM is great, people will move more and more data, hot data, into the memory, and along with our tier storage, people will leverage more of SSD as well. But in the meantime, people now see more disk, HDD, as a backup, as a backup storage. And it's not being removed from the picture. Yeah, just the functionality, the main goal becomes different. They serve a different purpose.
So let's start to talk more specifically about the use cases of Alluxio and how it works. In the current big data ecosystem, we have many frameworks, and they already leverage memory in certain ways, but file sharing among jobs is replicated to disk because replication enables fault tolerance, and there are always faults in distributed computing. Things just break. So what are the problems with needing to replicate to disk? Or perhaps we should start with, what are the prototypical types of cases, maybe Spark jobs or Spark plus MapReduce jobs working together, where we need to replicate to disk?
Yeah, so traditionally these systems, they use a replication to storage systems. They use replication to achieve the fault tolerance of the data. So what we are really doing here is that, along with the new announcement we had last week, what we're really doing is that we see, as you mentioned, there are so many different computation frameworks. In the meantime, there are all kinds of storage systems as well. So what you can see is that from the storage perspective, you have like Amazon, like S3, you have a Google Cloud Storage, you have EMC, you have NetApp, you have HDFS, you have a Gluster and Ceph from a Red Hat. So you have all kinds of storage systems. So what we're really doing here is that we put ourselves between these all different persistent storage, as well as the different computation frameworks. We put ourselves in the middle, and we bring a lot of benefit to the whole ecosystem, especially to our customers. So for example, to the upper layer, like MapReduce, like Spark, like Presto, all kinds of different computation frameworks. By working with Alluxio, they can really access data from any storage. What we say is we enable any framework talk to any storage, talk to any data from any storage. And in the meantime, we bring a lot of performance benefit. That's the benefit to the upper layer. And the benefit to the lower layer, similarly, we can, if a storage work with us, they can suddenly reach a lot of type of different workloads and applications. Anything supported by Alluxio on top of us, if a storage system integrate with us, they will be able to work with those computation frameworks. And in the meantime, we can also bring a lot of performance improvement. That's our benefit to upper layer and the lower layer. And another cool thing is that we call this the future-proven architecture, which means that no matter if you are a computation framework, and if you look at the ecosystem, and later on there may be another storage system coming up, and their company may buy another new storage systems. And by working with Alluxio, as long as that new storage also being plugged into the Alluxio, and that existing application will be able to access the data from the new storage system immediately. That's a strong benefit as well. Yeah.
Okay, so you mentioned the top layer and the bottom layer. These are essentially opposite sides of where Alluxio sits in the stack. So Alluxio is typically going to sit somewhere in the stack where below it you have HDFS or S3 or GlusterFS or all these other types of typical data storage, and then Alluxio is this layer between that layer and the higher level frameworks like Spark and MapReduce and Flink or these other types of data processing frameworks. So in order to get a finer idea of how Alluxio improves things, and just in case listeners don't quite understand some of the, or have some of the context, so talk about how like some sort of data science job perhaps, or some sort of multi-step job where you have multiple steps of Spark, or a step of a Spark and then a MapReduce job working in conjunction, and how that would work prior to Alluxio being in the Hadoop stack, and how it would work after Alluxio is involved.
Yes, that's a great point. So without Alluxio, we call our stuff memory-centric virtual distributed storage. Without Alluxio, these different jobs, they all interact with another storage systems. Actually, what happens is that normally people need to move the data from different places, from different storage systems into one single storage system. And then different jobs interact with that single storage system, right? So in this interaction, as you said, there are different jobs in the user's environment. The jobs could be written in one framework, could be written in multiple frameworks as well. So when they need to share the data, they have to read and write through a storage, as you mentioned, such as Amazon S3 or like HDFS or like EMC NetApp storage. And this sharing process is slow. It's slow. And the ETL process from different storage into this one single storage is slow, as well as complicated and time-consuming. So with Alluxio, what we can help here is that, so you put Alluxio between the computation frameworks as well as these different storage systems in the middle. We present a unified namespace to our upper layer, like Spark, like MapReduce, Flink, Presto. So they can suddenly access the data from different storage systems. In the meantime, because we have this memory-centric architecture, the framework has a very high bandwidth. We provide a very high bandwidth for the upper layer to interact with the data stored in our space. So then what we really enable is that we first of all remove this costly like ETL process, and in the meantime we provide a very high throughput to our upper layer to interact with the data. So make different jobs, different application jobs, potentially written in different computation frameworks to be able to share the data very efficiently at a high performance. So that's with us how it became differently.
Talk more about the API or the file system that the file system protocol that you use to present this unified namespace to different frameworks.
Yes, that's great. So for the API, we provide different APIs for people to access data from us. We have a native like file system API. So it's a Java-like file system API. Any framework or any application can interact with Alluxio using our native file system API, and that provides the best performance as well. And on top of that, we build other APIs as well. For example, we have a Hadoop compatible file system API as well. That means that any application or any framework, as long as they can work with a Hadoop file system API, they can work with us transparently without any code change. And that's the second example. The third example would be actually from Alluxio 1.0 release. We have a Fuse API as well. It's a joint work between us and IBM. So with the Fuse API, we enable much larger applications, much wider applications to be able to access data from us. So that's a Fuse API. And what's more interesting is that we also provide a alpha version of the key value API in the 1.0 release. So that means that people can also using key value interface to interact with Alluxio from 1.0. And we are working with very big trial users to improve this feature along the way. And I just gave several examples, and you can really think of at our layer, people can easily build more APIs on top of us to provide different ways to access data. And we really encourage the ecosystem to do this, to provide more ways to access the data from us. That means that they can access more data from different storage at a high speed. And we are seeing people are building different ways, more particularly suitable for them to access data from us. Yeah.
Okay, so what we've been talking about is sort of the interface between Alluxio and the things that operate on top of it. So let's talk some about what happens beneath Alluxio. So Alluxio has UnderFS, which is a file system that interacts with S3 or HDFS or these traditional storage systems. So what is UnderFS, first of all?
I see. So,
or was everything I said just accurate? Was that accurate?
Yeah, that's correct. Okay. So basically, we provide a very thin API from our side, from bottom of Alluxio to be able to interact with any storage system. So under storage system, from our perspective, is the layer below us, the layer below Alluxio, and from our position, we really want to work well with a lot of different under storage systems. That's based on the need from our users, and it's just very simple that you can see different users that they have different storage system deployed in their environment, and we just want to help them to be able to leverage that. So to make it simpler, just under storage system from our perspective is any storage the user have, and it can be performed as our under storage, and we can load and save data into it. And to our users, it's totally transparent, and we will handle the complexity to work with this storage system, these different storage systems.
So you handle the complexity regardless of whether it's S3 or HDFS or something else. But what are the commonalities between those different types of interactions? Like UnderFS, I imagine the UnderFS interaction between S3 has some similarities between how UnderFS interacts with HDFS, but I imagine there are also differences. So maybe you could give some granularity on what is the relationship between UnderFS and these different storage systems?
Yes, definitely. So yes, they are different. They have different properties, and they have different performance characteristics. And we would normally leverage the existing infrastructure in our users' environment, and then we enable more ways to access the data for that particular storage in our user environment, and provide a much better performance. And definitely for different storage systems, like Amazon S3 has a different property than HDFS, have a different property than like Ceph cluster cluster file system. So that's up to the use cases in most cases, as well as up to the user's environment. If they really value the performance of that under storage systems, so they may buy very like a high performance under storage. If they don't care, they may choose a cheaper solution. That's more up to our users, and in the meantime, it depends on their requirements. From our side, definitely with different under storage systems, we have some different integration as well. For certain under storage system, we have a more primitive integration because it's early. For certain other under storage systems, because a lot of user requests, we may have a deeper integration. With a deeper integration, definitely it can improve the performance as well as the reliability. But we have many progress undergoing on this front.
Now that we've talked about what goes on above Alluxio and what goes on below Alluxio, let's talk about Alluxio itself. So tell me about the Alluxio system architecture.
Yeah, so we are a scale-out architecture, and we are scale-out memory-centric architecture. So basically, to simply speaking, it's logically it's just a single master architecture with the worker daemons running on the every worker node, and it's like many other scale-out architecture. But the difference is that in our architecture design, we focus a lot on the memory-centric front. In the meantime, that's one major difference. In the meantime, we have a lot of features in our space. For example, like tiered storage, which I mentioned earlier, which means that, yes, we focus on the memory performance, but we also leverage other tiers as well, like SSD, HDD. And this feature has been running in our in the production environment for more than a year for some cluster more than 100 nodes, like Baidu. In the meantime, like we also do like master fault tolerance to guarantee there's no single point of failure. That's the high level of our architecture.
Okay, so Alluxio has a master and it has some number of workers, and each worker has access to a RAM file system. Could you describe this architecture in a little more detail and give me an idea of what the responsibilities of the workers are, what their relationship is to the master, and so on?
Yeah, no problem. So for the worker, like say on every worker node, we run a Alluxio worker daemon, which manages the local space, like local tier structure, and as well as it reports the status periodically to the master, as well as responds some remote I/O requests. That's a worker daemon. And beyond the worker daemon, we also run a RAM disk on every single worker machine. And whenever there is a data locality, our Alluxio client is going to access this RAM disk directly to get a full memory performance. That's the worker part. And from the master part, our master node daemon manages or keeps tracking the status of all the workers' status, as well as understanding where the data is, the data location information, and sometimes it will respond client request to ask for the location information of the data. Of course, it's handle metadata.
How often do nodes fail in a typical cluster?
Yeah, so there are different types of failure. So like if you say machine failure, it's what we are seeing is similar to how other company, any distributed system is seeing. So, and we have mechanism to recover from that. For the system itself, for the software itself, it depends on whether you are using a stable release or you are using a master branch, cutting edge master branch, and this we heard what we heard from our users people are pretty happy about our software quality. Like say, for example, like Baidu, they have been running us in their production for more than a year, and their pleasant experience, which we are very happy to hear. Yeah, but definitely we're also constantly improving the system from every single perspectives, including the stability of the system.
So we'll talk more about some of the company use cases later on, including Baidu. I want to talk more about failures and what you do around failures. Alluxio's idea to prevent failure, well, I shouldn't say to prevent failures, to deal with failures, is similar to Spark's idea, which is the lineage-based recovery. What is lineage-based storage?
Yes. So it basically simply means that like lineage just means that the relationship among different data. Like say one concrete example would be like say you have a program, it reads a bunch of files and writes a bunch of files as well. And this is a lineage information in Alluxio. By knowing that information, if any data got lost, Alluxio will be able to relaunch necessary computation jobs to get the data back. But that's just one way of how we handle this. We provide different options to our users, which, for example, like you can do asynchronous persistence and use lineage to get the fault tolerance, or you can use like synchronous persistence, like which means while writing into Alluxio also synchronously flush the data into our understorage, which also provides the reliability of the data. That's another way. And a third way is actually like in some cases, our user doesn't care the reliability of certain data. So they may simply choose, okay, I want to do the asynchronous flush, but if some data got lost because of machine failure, sure, who cares? So in some use cases, it's like that. And there are even more interesting use cases. Like say, for example, in some industry, they have a regulation. They couldn't save the data to the disk, and they can only put the data in memory, and we can help them in that case as well. So it's more like we provide a pretty flexible architecture for people to choose, provide them options for them to choose the ways best suitable for them, makes most sense for them. So that's the way we look at this.
So that's very interesting. I want to touch more on the lineage-based idea because I think this trend of lineage-based operations is an important concept in distributed systems. You see it in Spark and you see it in Alluxio. I imagine we'll be seeing it for a long time. So for people who may be newer to distributed systems, they may not understand, when they're thinking about like just replicating the data versus having the lineage and recalculating and in the event of a fault, like if you compare the simple data replication, if you have a fault, you've got the data replicated so you can restore the data. In the case of a fault in a lineage-based system, it seems like that would be a lot more complicated. You have to take all these past operations, recompute the data in order to get it back. Why is the lineage-based operation actually cheaper than just replicating that data?
I see. That's a great point. So what made it possible or attractive is that in the big data world, the data volume is really high. And replicating that, the cost of replicating it is much higher than recording the lineage information. And I agree with what you said, that to handle this lineage information well is not an easy job. It's hard. What we are doing is that like we provide the API for the upper layer, basically the framework layers, to leverage this functionality to do the integration. And when they are if any computation framework integrate with us for that particular feature, so that basically means that any application on top of that framework will be able to leverage this feature transparently. So even though the system itself could be system itself is hard, but most of the complexity is handled by the computation framework developers instead of application developers. We try to hide the complexity from the upper layer as much as possible. But it's also a ongoing effort. You can always make it better and easier for the upper layer to consume. Yes.
Why is it cheaper to maybe I'm just rephrasing the same question I just asked, but maybe I'm naive. But why is it cheaper to do this lineage-based strategy rather than just replicating everything in memory? Like, couldn't you just have 3 copies of everything and have them in memory on different nodes?
Yeah, you can. You can do that in some cases. But say, as I said, like you have this big data environment, like your binary program may be like 100 megabytes, right? And the data that program is dealing with, the input-output, the output data could be like hundreds of gigabytes, and it's 1,000 times different. And then replicating that, first of all, you will see you will reach the bottleneck of the network. That's one issue. And the other issue is by replicating it in memory, like even though memory price is going down exponentially every year, but you still have limited memory space. So by replicating it, you will consume a lot of memory space. That's a economical choice people can make. But by using our way, that issue doesn't exist.
Sure.
Yeah.
Okay. So in the event of a failure, and if you need to recompute from lineage rather than recomputing from a replicated type of system, how time intensive is it to recompute data from the lineage?
That depends. That depends on the application and depends on the. It's not an easy issue. It's not an easy issue. But we do have ways to provide some bound from that perspective. But in the meantime, I think this lineage feature we started, it's only one part of the system. Like if you look at the whole system itself, or if you look at the new announcement we made, it's now the system has progressed tremendously over the past since the beginning of this project. Just give you some numbers. For example, like one number. Let's just talk about the number of commits. Everyone can understand it. So now the system has around 13,000. I think it's around 13,000 commits. A year ago, it was 3,000 commits. So over the past year, this increased like 5 times. And the community also grew very fast as well. So a year ago, we had maybe around 50, 60 contributors. Now we have more than 200 contributors. The growth has been tremendous, and we are pleasantly surprised by this. And we believe that with this growth, the community, and we, along with the community, will add more features and more features into the system, which brings more advantages or feature use cases to our users. So that's what we see. And back to the lineage point, that's the initial feature we had, and now we have so much more. Like the one we discussed, like the tiered storage system, like the one we discussed, like the unified namespace. So, or the different ways to access the data, like key value, like Fuse API. It has been amazing, to see this progress.
Yeah. So, I saw several talks as I was preparing for this interview, several talks that you gave, and in each of these talks you talked about the overarching goal with Alluxio, and it seemed like, many people asked you this question: what is the goal of Alluxio, formerly Tachyon? And at first glance, maybe the goal, you might think, the goal is just like this in-memory computing thing, but it's actually a little more abstract. So talk about the goals of Alluxio.
Yes, definitely. So I think as a system, the number one goal is to bring more benefit to the ecosystem. So the way we do this is that, as I mentioned earlier, before us, there are two layers. One is the computation, the other one is the persistent storage. And there are issues with this, especially along with the growing on both sides. You have more different type storage systems, you have more different type computation frameworks. And in the meantime, sometimes, in many cases, performance is the issue. And as I said, we're bringing this new layer, which abstract these under storage systems and provide a unified namespace to the upper layer to make the upper layer computation frameworks as well as applications easier to access data from any storage systems. So that's the benefit. In the meantime, we provide a much better performance. And our long-term vision is just to make this become the de facto standard of this unified data access layer. And in the meantime, provide tremendous performance improvement to our users. That's our goal. And in that case, we can bring benefits to the whole ecosystem, to the different frameworks, to different storage systems, and more importantly, provide to our users. That's the way we see this.
So let's talk about some of those benefits in practice. So for example, Alluxio obviously speeds things up, and that propagates to the people working at the higher end of the big data stack. We have data engineers and data scientists. How does the job of a data scientist or a data engineer, perhaps working with Spark or some other set of tools, how does their job and their workflow change in a big data stack that is post-Alluxio?
That's a great question. So I think there are a lot of perspectives, but there are some major ones. For example, like from the data scientist perspective, like on one side, Alluxio makes their life much easier. So because it's a unified namespace, they don't need to explicitly move data anymore. So they just simply tell Alluxio, I want to access this data, and then it will just be able to access it. That's one thing. They don't need to wait for 2 months or a month to let people to transfer data for them. That's one side. And the other side, for any of this type of data access, after the performance will be much better. You saw like the Berkeley wrote an article maybe 2 weeks ago, published on DZone. So the article says that making the impossible possible with Tachyon. Back then we still talked Tachyon with Alluxio. So accelerating Spark applications from hours to seconds. That's tremendous. So basically, you can think of like previously a day, they need to, like half of the day, their data scientists need to wait there to get this prepared. Now it became seconds. So this tremendously changed their working behavior to make it much more efficient and bring them competitive advantage in their space. So that's basically, in short, one thing is make their life much easier and improve the performance tremendously. And I think this unified layer, based on like one of my PhD co-advisor, Jan Stoica, he's also he's the co-creator of Spark as well. So he said, it's also in our press release, he said Alluxio to storage is more like, can be acknowledged to be internet protocol layer, IP layer to internet. And we can enable faster innovation and make people's life much easier. So that's the way we see it.
Yeah, what I find interesting, when you go from taking an hour to run a Spark job to seconds, kind of traditionally, like at least when I was in school 6 years ago, we always talked about things in terms of Moore's law and having this very predictable, 18-month cycle of compute time or number of processors on disk doubling or on a chip doubling, or however you want to phrase it. Compute power doubles every 18 months. But I feel like perhaps that set of trends was constricted by what occurred on the hardware layer, because you had to have all these people moving in lockstep in order to orchestrate the hardware progressions. But when you make an advance at the software layer, it seems like perhaps you need less coordination, and therefore you can get bigger step changes, such as what we're seeing with Alluxio. Does that idea resonate with you, or do you think that's crazy?
I mean, the hardware trend is always look at the whole industry. So it's improving from many different perspectives. You always have a lot of innovation on the hardware side. But in the meantime, the software also will adapt and improve themselves. So, like take us example, like we saw the trend of the DRAM. So we leverage the trend, will provide much better hardware, software, and innovative like architecture to the industry. And what we are seeing is that we just collaborate with the whole ecosystem to bring more benefit to our users. So that's the way we see it. Yeah.
Okay. So with Alluxio, you've mentioned there is still cases where you do want to store to disk. Let's talk about that in a little more detail. So when would you still want to? I'm a data scientist. I'm a data engineer. When am I still going to want to use disk storage despite Alluxio? Yeah,
so you still want to use it. Like say you have a lot of data you want to put on disk in the end. For example, like that's our under storage basically in the Alluxio world. And Alluxio always works with at least one or more under storage systems, not in most cases. So, I mean, we really want to work with the state-space storage systems well. And the goal is not to replace them. The goal is to work with them and to improve the whole stack. That's the way we see it. Yeah.
Okay.
Yeah.
Let me just close off with one other question then. Let's see. So what is the future of the Hadoop ecosystem, and how does Alluxio fit in?
That's a great question. So Hadoop ecosystem is a very big ecosystem, and there are a lot of pioneers in this ecosystem. So how we are fitting together is that with Alluxio, we can bridging. First of all, of course, we can improve the performance. But on the other side, we make people's life much easier, as well as bridging the traditional world with this ecosystem. But in the meantime, from our perspective, Alluxio also works with a lot more different types of ecosystem as well. That's what we see it. But come back to the Hadoop ecosystem, we will keep improving and further to make our users experience better by improving performance and improve the usability of the system.
And where can people find out more about Alluxio and find out more about you?
Oh yeah, definitely. If they Google Alluxio, they can go to our websites, they go to our project websites, company websites. We have a lot more information there. In the meantime, if you are interested, of course, feel free to contact us as well. We'll be happy to help whenever it's suitable.
Okay, great. Well, HY, thanks for coming on Software Engineering Radio. It was great talking to you about Alluxio, and I wish you the best of luck. I'm really happy with your project.
My pleasure. Thank you very much, Jeff.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.